All right, howdy. So what I'd like to do is I'd like to look at this case to talk a little bit about Boyle's law, basically. So we're going to look at a case where we're not going to let this gas heat up. It's in the cylinder, but it's going to be kept at a constant temperature. And then we're going to take this piston, put it on top of that gas, and let the piston fall. And so it's going to fall from being at 20 centimeters and going down to 10 centimeters. Okay, and that's going to increase the pressure of the gas. And after it does that, we can figure out by how far it's compressed how much this piston weighs. But the first thing we have to do is figure out the pressure of the gas, and we're going to use Boyle's law for that. That is the initial pressure times the initial volume is equal to the final pressure times the final volume. Yeah, that's just saying the internal energy of the gas is not changing. That's all Boyle's law is saying, is this gas has the same amount of energy inside of it, and it's just changed its volume somehow. Okay, so that's more or less all we're looking for here. So now, in order to do that, what we need to do is we need to, just plug in some numbers at this point. This is fairly simple because we want to find this PF, and we have things that we can turn into VI and VF, right? So the volume is equal to the area times the height. The area is 14.7 centimeters squared on both sides, and the initial height is 20 centimeters and the final is 10 centimeters. So we have the pressures and the volumes. So the pressure is just standard pressure, which is 100 kilopascals. I really screwed up the accent on that, but that's okay. And 14.7 centimeters squared times the initial height of 20 centimeters is the volume. Then we've got what we want. PF is equal to, or PF, so this is equal to PF times the other volume, 14.7 centimeters squared times 10 centimeters. Okay, so we look at that. This is where not doing multiplications until we have to is good, because that area and that area are the same, so we don't have to worry about them, they cancel. And we see here the centimeters cancel, and this is 20 and this is 10, so PF is just the 100 kilopascals times 20 over 10, or 20 times 2, which is 200 kilopascals. So not something that should drive you crazy. Okay, so that's sort of the first part. Now we have that pressure, this final pressure. We can figure out how heavy that piston is. And we can do that using a free body diagram like this, right? We have the weight pushing down and the force from the pressure pushing up. I guess that's coming from down at the bottom there. So this is the force from the pressure, and this is the weight, and this is the other direction, y. This is the direction we call z. Z is up. So basically, if we read that free body diagram, we have everything going on in one direction, right? So we have F going up, and that's E, and minus the weight going down, which is equal to 0. They balance. Once again, this is Newton's first law problem, so the weight and the pressure balance, which means that the weight, mg, is equal to the force, which is the area times the change in pressure. The change in pressure is just the final pressure minus the exterior pressure, which is the atmospheric pressure, which is just this number, 100 kilopascals. The same pressure the gas was before it was compressed. So that's not going to hurt us too much. We have mass is equal to 9.8, or mass times 9.8 meters per second squared is equal to 14.7 centimeters squared times 200 for that guy and 100 for that guy. So that's 100 kilopascals there. Okay, so then the mass is equal to 4.7 divided by 9.8. 4.7 divided by 9.8 is 3 halves. So that's 3 halves. Oops. That's the end of the screen. Doesn't tell me where the end of the screen is. Maybe I can tell the difference between this black and this black. I'm not sure. Let's see. So we have meters per second squared down here. We have centimeters squared up here. So that's 1 over 100 squared meters squared. All right. And then we have 100 kilopascals. So that's 100,000 pascals, and a pascal is a Newton per meter squared, which is a kilogram times over meters times second squared. Okay, so let's see. This guy cancels and that guy cancels, and we've got 2 of these in the bottom and 1 of those in the top. And that's 1 over 100 squared is 1 over 10,000 squared, so I can cross off 4 of those zeros. So I have 3 halves times 10, which is 15 kilograms. 15 big kilograms, that is your answer. All right, so what have we done here? Well, first we went through and we used Boyle's law, which is basically just conservation of energy, to figure out what the final pressure was. And the only thing we had to bring in is the fact that we started at atmospheric pressure. Atmospheric pressure is 100 kilopascals. Or what in the atmosphere, if you want to call them atmospheres, but it's easier to use metric units. So then we just plugged in all our data, got a number. Not a big deal. Here we had to draw out the mass of the piston because we're using Newton's first law. They're still applicable, those laws. And then we had to just use the definitions of each thing. So we had the weight is equal to mg. The force from the pressure is equal to A delta P, the difference between the pressure inside and out. We talked a little bit about that with buoyancy. Now we're using it here directly. Then we're plugging in numbers again because we have all the numbers, and that ends up giving us the answer for 15 kilograms. So first we use Boyle's law, which is a kind of conservation of energy thing, and then we use Newton's first law, which is balancing forces, and we're done. So a quick little romp through the beginnings of thermodynamics for you today. All right. Well, thank you very much for listening. I hope you're having a great time wherever you are, and I will talk to you soon. Bye now.